So the other thing I wanted to show you is this project, CNET 105. So you start on the 141 page. Well, you start at samsclass.info here. Then you click on 141, and that will take you here. And then you click on projects, and that will take you here. And last time I demonstrated these projects, and now I want to demonstrate the 2-time pad. Now, we've talked about this. If you have a 1-time pad, that is essentially the perfect encryption system. And the Russians used it in World War II. So what they would do, they would just have somebody type random words on a keyboard. And they'd just fill pages and pages of this. And then they'd make 2 copies, and that was the pad, the 1-time pad. And if you have enough of this, you can now encrypt. You use each letter to encrypt 1 letter, and you never reuse any part of it. So you have many, many lines of this. And so you encrypt your message with these lines. You never reuse any part of it. There's no mathematical pattern, so it's perfect. But the problem is, how do you do this before computers and before printers? Well, the way you did it was with a typewriter, an impact typewriter, printing on paper, and you had carbon paper, and you have another piece of paper behind it. So you get 2 copies. But then what happened is they were doing badly in the war. Hitler invaded, they had trouble, so they needed more. So they started putting in stacks of carbon paper to make like 4 or more copies of the same pad, so they could have more pads. Now the problem is, if you reuse the pad more than once, it destroys the whole thing, which is not very obvious, but that's what we're going to see. It becomes vulnerable to this thing called the crib drag attack. So first, let's play with the 1-time pad. So here, I put it in Python. In this case, the key, instead of being random letters, is going to be a sentence, which is kind of unprofessional, but this is so you can see it. You could use this for a key, but then it's not perfect, because there is some pattern to this key. However, aside here, I'm going to encrypt this text 4, 4, and 7. So all I do is define the key in the plain text, and now my ciphertext starts as an empty string, and I just go through all the letters of plain text, turn them into a number, the ASCII number with ORD, and take the key bit and turn that into a number, and then do XOR between them. This is how you do XOR in Python. And then I turn it back into a character. So I take the capital U and the capital F, I XOR them to make the first bit of key space, and then I print it out. So if I run this, Python 3 pad1.py, you see here's the key, or here's the message, 4 score and 7. Here's the key, unbreakable, awesome. Here's the ASCII numbers, and here's the encrypted value, 13, 1, 17, 0. This is the output. So here's the actual ciphertext. Just a bunch of hexadecimal bytes created by XORing them together. And if this was a random key string and never used again, there would be no way to break this, because there's no mathematical pattern at all. There's no place to get your teeth into it. And for centuries, this has been understood to be a perfect unbreakable system. But now we're going to crack it, because we're going to do a crib drag. And so I've got an example script to get you started here. So I'm going to load that and call it, say, crib1. I'll just call it crib.py. All right. And so what happens here is, all right, whoops, I got to use this. Okay. So here, here's the inputs. Here's the first ciphertext and the second ciphertext. And I don't know the key. So I'm just going to guess the key by putting the word "the" and a lot of dots. So I'm guessing maybe it starts with the letter "the." So then I'm just going to calculate these XORs, just like before, and it's going to print out the answer. And let me just show you how this runs. If I run this one, Python 3, crib, okay. So here's the key, and here's the protocol, nev and u. Now, if I guess the key wrong, these will turn into random bytes, and often will not even be printable. So that's what you see over here. When the key is wrong, you just get garbage for the plain text. But if the key is right, both of these will be readable. And it looks like it is true. The key starts with the letter "the," because both of these, the first 3 letters, are actually readable. So now, the point is, this is why it's the crib drag. If I can guess the next letter in any of these 3 rows, I can make progress. So I have the next thing here is probably a space. So if that's true, the key, letter 3 is a space. So I guess key letter 3 is a space. All right, now I've got U apostrophe. So this is like an L or an R. Here I've got neva. Now I don't have anybody guess this. That could be anything. But here, this is probably never. So that's probably an R. So I can guess a 1 in location 4 is an R. All right, now...
But just for P1.
I got that one letter. Now I have never. Now I could probably guess the next thing here is a space. So that would be another way to go. Another thing I could do is if this is U apostrophe L, this is probably an L. So either one of those is pretty good guesses. I'll go with the second one. 2, location 5 is an L. All right. And that created a space here, and the U came after the Q. So I could have guessed any of the 3 in that case. So now this probably is a space. 2, location 6 is probably a space. All right, and that's what the crib drag attack does. The fact that you have 2 messages encrypted with the same key mean you can keep guessing any one of them. And without a computer, this was all before computers. Even without a computer, you can crack it. And the Nazis did. So that's the crib drag attack. That's what I wanted to show you. And as far as getting points here, the first one here, you just have to do the encryption with a known key. The next one, you break this one, and one of these sentences is going to tell you the flag is something. So you'll have a flag. And then I got harder and harder ones. And here, they're both encrypted with the same key, and so you're going to have to guess what the key is. And I think for this one, but you don't have to guess just the key. If you guess correctly, now let's try something else back here. Suppose I guessed the, and the was not in the key, but it was down here. If I flip 2 of these, if I put never up top, let me do that. I'm going to put never up top. So the key 0 is N, key 1 is E, key 2 is V, key 3 is E, key 4 is R. There. I put never up here. And what happens is the key appears down there. The right key is new Q. The right key is the QU. But when you put the text up here, it's there. So if the word the appears anywhere in either the plain text or the key, I'll be able to see readable stuff appear. So that's why it's easier than you might think. So if the word the appears in the key or in either of the messages, then I'll get a portion of this to turn clear. And so what I did to crack this is I guessed keys like this. Let me just get, I'll just get a text editor. I'll get rid of this. I guessed the space, a bunch of these. And then if that fails, I put another space here, another 2 spaces here. And then I think you need 4 of these. There. And the next one to repeat it. If the word the appears anywhere, then one of these will cause something to become readable. And I have a series of 5 letters that will become readable. So I'll be able to spot part of a word. So that's why it's easier, even if you don't have any information, you can just guess a common word and try this. And if that word appears anywhere, then some little piece of it will be readable. And then you can start guessing a letter to the right or the left and expand. That's the crib drag.
You're using the principle of modularity, no? Because you are moving one space.
Yeah, and I know it's all going to be wrong, but somewhere in the message it will be right. So some group of 5 characters will become readable, and then I can move from there. That's why it's good to have an interactive program like this where you can guess things and go back and try other things. But it's interesting, and they get harder and harder. This one's worth 50 points because it's a lot harder. But anyway, they should all be perfectly unbreakable. You should never get any of them. The fact that you use the same key twice makes it possible. And in fact, so easy that you could do it before there was a computer. So that's why people are afraid of cryptography. You can have a very strong system, and if you make one mistake, it's destroyed. It shatters like glass. It's much, much weaker.
But don't cryptographers use logical proof? Don't they?
Well, the mathematicians do, but in practice, the people that design things and the people that fight wars make approximations
Okay.
and do things like this. Like, you're only supposed to make 2, but we need more. Well, make more. What harm could it do?
So it's the distance between the person who creates and the person who uses.
Yeah. That's why, there's an old statement, in principle, there's no difference between theory and practice, but in practice, there's a difference. I mean, if the math looks good, but when you really do it, you never do exactly what the math said. You have to make approximations to get the job done.
Yeah.
And even making what seem like very reasonable approximations can ruin it. It's more dangerous than you think to do almost exactly what they told you. That's all right. So we check for comments in the Twitch. Okay, so I'm going to stop this recording.